Good morning, everyone, and welcome to today's presentation on selecting your pressure regulator in 5 steps, brought to you by Swagelok, Indiana, Cincinnati, supplier of critical fluid systems throughout Indiana, Central Kentucky, and Southwestern Ohio. I'm your host, Jorge Jimenez, Director of Sales here at Swagelok, Indiana, Cincinnati, and I'm joined today by leading regulator expert, Mr. Wouter Pronk, who has kindly offered to present today's webinar on regulator selection. This session will be recorded, and we encourage everyone to please ask questions throughout the presentation. You can do so by clicking on the Q&A button and typing your questions into the chat box.
Hi, you doing good?
I'm doing better.
Good.
Mr. Mike Peckrell, a resident field engineer, will then address your questions to Walter. I would also like to point out that we'll be raffling off a Swagelok Jetty 10-ounce tumbler for everyone that submits a question during the presentation. The winner will be notified via email after the presentation. As some background, Walter has 27 years of experience working with pressure regulators. He is based in the Netherlands outside of Amsterdam as a senior field engineer for Swagelok. So for now, let me hand it over to Wouter Pronk to walk us over the presentation.
Okay, thank you, Jorge. Okay, good afternoon, everybody. I will be presenting from the Netherlands. It's like Jorge said, I'm based in the Netherlands. I will do this presentation. The presentation will take approximately 35 to 40 minutes, based on the questions. There is a Q&A in the end, so please take the opportunity to ask your questions. Microphones and cameras are turned off, so please keep them turned off and use the Q&A so that everybody can hear what we try to tell you. Let me introduce myself first. So my name is Wouter Pronk, Dutch, 100% Dutch. I'm a pressure regulator tech lead. I was sales manager at RHPS. That's a private company which was acquired in 2010 by Swagelok. And since then we manufacture the pressure regulators on the Isle of Man in Swagelok facility. I'm focusing on training on pressure regulators, so 27 years of training. I have also a group of global pressure regulator specialists, which I mentor and which I train as much as possible to serve everybody and basically transfer knowledge into people. That's a biggest objective at the moment. So thanks for being part of this objective. Today we will talk about how to select a regulator in 5 steps and try to avoid mistakes. So step 1 is be aware of the correct process information. So pressure, temperature, flow and material. So what do we want to control? Do we want to control upstream or downstream pressure? Realize natural behavior and performance of a regulator. So don't think that we can create a regulator which is set at a certain pressure and will keep that pressure without any fluctuance. So log up, supply pressure effect and Droop will be subject today. Select the correct loading element. So are we going to use a spring-loaded regulator or are we going to use a mix of both or a dome-loaded? And a little bit of troubleshooting, filtration and safety valves. So what's really important, so if you want to use a pressure regulator, it's important that we start with all the information we need. Without all the information, we can't do a proper selection of a regulator. So we want to know, are we going to control a liquid or are we going to control a gas? If it is a gas, we must realize that a pressure regulator can handle much more flow of a gas with a low density than it can handle a gas with a high density. So think about the difference between air, nitrogen and hydrogen. Hydrogen will do approximately 3.8 times more than air. So if you select a regulator which should do by example 380 normal cubic meters of hydrogen, you can compare it with a regulator which can do 100 normal cubic meters of nitrogen. So please forgive me about the units I use. I'm very 100% used to the normal cubic meters. and I try to use the PSIs as much as possible. So how do we select regulators? I like to work with flow curves, and we will talk about flow curves more and more and more, because flow curves are the best tool which can be used to select regulators, because it gives basically what you see is what you get. It's important to know what you can see in the flow curve, and I will repeat it several times again today because it's an important tool. In the flow curve, you can see two axes. We have the y-axis, which is the outlet pressure, and we have the x-axis, which is the flow in normal cubic meters in standard cubic feet per minute. What are the things we all need to know? We need to know the maximum and the minimum inlet pressure of a regulator. So think about a cylinder. It will start at 3000 psi approximately, but it will decline to a lower pressure. I still have to find the first cylinder which will stay at 3000 psi, so it will decline. And if the pressure declines inside the regulator, you will see immediately the supply pressure effect. Now, what is supply pressure effect? Talk about it later, but if this is your pressure, if this is your inlet pressure and this is your outlet pressure, if your inlet pressure drops, your outlet pressure will go up. So it's important for us to know the outlet pressure and how accurate it must be. This to select the correct diaphragm size. Is the outlet pressure also related to the flow capacity we need? So do we expect that the outlet pressure is the same at all the flows? So the minimal flow, normal flow, the maximum flow. Sometimes processes are, the specification of a process are given in the minimal, normal and maximum flow. We also need to know the preferable flow the process needs. So is it given in standard liters per minute? Is it given in normal cubic meters per hour, in standard cubic feet per minute? Or maybe in a mass flow. And in a mass flow, we recalculate it into volume flow, because that's where our calculations are based on. So in liquids, we like to work with liters per minute, because it's not compressible. So thinking about the flow curve, where do we want to be in the flow curve? Which regulator can we select? We like to see if this is a typical flow curve, this is the flow. And I like to be in the most horizontal part of the flow curve. So in this part, I don't want to be in the first part where we see the lock up, to be explained later, and I don't want to be at the end of the flow curve where we are in choke flow. That's not the place to be. So I like to be in the middle flat section. So talking about a flow curve, how do we select the flow curve and how does it work? And again, at this side of the X, we see the outlet pressure given in PSIs. This side we can see it in bars, and believe it or not, in Germany the bars are at the left side and the PSI at the right side. And on top we see the flow, the normal cubic meters per hour, and at the bottom side we see the flow in standard cubic feet per minute. Really important to know, these flow curves are made for nitrogen or with nitrogen. So on our flow test benches, we work with nitrogen. So we can't work, and we have no flow test bench to make the flow curves in hydrogen. So in a flow curve, you see several lines, which are the flow curves. So if I want to select and to see if a regulator I want to use can do the job, I have to find the correct flow curves. You see a lot of lines in this flow curve. Maybe confusing, but it's not that difficult. So I just want to start an example. So what is the pressure drop? So if we start using a regulator and there is no flow, and we increase the flow from 0 to 150 normal cubic meters per hour, what will happen with my outlet pressure? And I start setting my regulator at 250 psi static situation, and the inlet pressure of my regulator is 507 psi. So how do I select and how can I see what's happening with my regulator? So first of all, you try to find the correct flow curve, because lots of lines. Which is the correct one? It's not that difficult. Set pressure was 250 psi. That's at this axis. So hey, that's correct. That's the one we need. Inlet pressure was 507 psi. This is the one we need. So we found the flow curve. Then find the pressure at the start point. That was the set pressure in a static situation. So it's 250 psi. Point. Find the point on the flow curve for 150 normal cubic meters per hour. And this is where a lot of people make mistakes, because very confusing. We have got the normal cubic meters, but also standard cubic feet per minute. So this is the normal cubic meters. So that's a line we have to work with. Then we read the pressure at 150 normal cubic meters per hour flow, because I started at this point at no flow, and I follow the line to the point of 150 normal cubic meters, so I can see what happens with my pressure. It drops from 250 to approximately 220 bar. So the difference between the starting point and the end point is approximately 30 psi, which is in the Netherlands a 2 bar. So if you want to know the pressure drop in bars, you can use the other side of your flow curve. This is a simple example from how to use a flow curve. Don't be afraid of it. It's a very nice tool. And for your information, online we also have our flow curve generator. So where you can put in your information, and it will, in the regulator you want to select, and it will show you the flow curve. So that's a theoretical flow curve. Most flow curves we show in our documentation are flow curves which are really made by a flow test bench. But on the bigger sizes, we are not always able to do this. The flow curve generator will give you the opportunity to select a flow curve which is really according to your process. How do you want to control the regulator? Do we want to control it with a diaphragm, or do we want to control it with a piston? Regulators on the low pressure are controlled and are measuring the outlet pressure with a diaphragm. But regulators with a high outlet pressure are measuring the outlet pressure with a piston. Why is this? Because of the area of your diaphragm and all the force which works against it from the outlet pressure, there is a lot of force on top of the diaphragm. So we need to compensate that with a spring, which we use to set the pressure. If this outlet pressure is too high, we can't handle that outlet pressure. So we need to make the sensing element smaller. And the only way we can do that in the standard regulators to use a piston with a smaller diameter. So why do we use the piston? And when do we use the piston? We use the piston to control higher pressures and outlet pressures. If I select a regulator, I prefer to have a regulator with a very large diaphragm and a very small seat. So the diaphragm as big as possible and the seat as small as possible. And why? Because it gives you a better repeatability and a more sensitivity. You can imagine that if I set a regulator at a certain point, at a certain process data, and there will be a change in the inlet pressure or a change in the flow, it will run away a little bit from the set pressure, which you can see in the flow curves. But if we go back to the original situation, the repeatability of a regulator will show that it can come back to the original state. And if we talk about sensitivity, then it's important that the regulator can respond on small changes in the process. Think about a blanketing process where we talk about millibars or small inches of water of change. We don't want to see big changes in there. So I like to have a very nice and big sensitive regulator. So it's a standard regulator. This regulator is a standard regulator, but we have the same versions with bigger diaphragms like this one. And you see it's a big diaphragm, so we can't control a very high outlet pressure. Big diaphragm is always related to lower outlet pressures. Temperatures, something which really is important for us. So think about an application where we reduce a lot of pressure. You will see Joule-Thomson effect. And the Joule-Thomson effect is basically where we reduce pressure in a gas. And if there is a reduction in gas, we need warmth or heat to make it basically we need heat to reduce the gas. So we will take the energy and the power from the outside. So we will cool down the regulator. And if the regulator cools down, you will see condensation. So the picture I shot over here was taken in Brazil, high humidity. The regulator was reducing CNG gas. And if you think about CNG, methane gas, and this one was reducing from 260 to 20 bar, the temperature will drop from 65 to 20 Celsius or minus 68. So that's a lot of pressure drop. We can calculate the Joule-Thomson effect, and we can also calculate the heat we need to compensate this. Material compatibility is really important to select the correct materials, because in our regulators we use materials like elastomers, diaphragms, we use O-rings, and also we use like several materials. Where do we see the issues with compatibility? Where I just talked about Joule-Thomson effect, we have to realize that the regulators must be built with the correct materials. So if you really want to use a regulator in very low temperatures, maybe we have an issue with the elastomers and the polymers. We have to be sure that the fluid is compatible with the materials. So this is a nice example where the diaphragms were not compatible with the material. So it started swelling, it was damaged. Pressures. If you think about high pressures and big diaphragms, we have to be sure that we design and the design is good enough for higher pressures. So compatibility does not only stop with the chemical attack of materials, but also in the situation where the materials are not compatible with your application. What about process conditions, erosion and cavitations? I like to show this one, and I'm not really proud about it, but this customer was using this back pressure regulator in a situation with methanol injection system, and the damage you see on this material was caused by erosion, and it was only a few hours, and it was in this state. So this is a component of a regulator which was basically selected in the wrong way. Some people say, why do we have that low numbers in our documentation? The documentation shows the numbers which we tested. So the temperatures and the temperatures and the pressures which we mention in our documentation are basically values which are tested in our labs. Some people say, if I go for elastomers like EPDM or Phyton or Calrace, I can see in the documentation from the supplier, I can see different numbers. Yes, but those numbers are normally and very often based on environmental conditions and not on conditions under high pressure. So we tested in environmental chambers, we tested the regulators and the materials at temperatures and pressure. So sometimes the numbers are a little bit lower than people expect. So are we controlling? Sorry.
Hey, what would cause cavitation in a regulator?
Cavitation in a regulator, that's basically if there's a big pressure drop, and it's only in liquids. If there's a big pressure drop, you get implosions, and the implosions eat away the material. It's erosion by cavitation.
Okay.
Welcome. Another step, are we controlling upstream or downstream? So this is a simple process. A lot of people look at the process like this. This is basically my process, and the process is asking for the maximum capacity of flow. So it's not us giving you the flow. No, the process needs a certain flow, and we need to find a regulator which can handle the flow, and which can handle the flow under the worst scenario. So if this cylinder, and that's why I made this cylinder in there, if this cylinder drops from 200 bar or 3000 psi to a much lower pressure, then I have to calculate the size of this in that regulator. I have to size it on the worst case scenario. The same with the back pressure. In most cases we see or a pressure reducing regulator or we see a back pressure regulator. A pressure reducing regulator is controlling upstream pressure, so it's controlling the pressure in the process, and a back pressure regulator is controlling the pressure, maximum pressure inside the process. If the pressure is too high in the process, the back pressure regulator will open. If the pressure is too low, the pressure reducing regulator will supply the gas. So it's important that we know what are we controlling, and we see a lot of misunderstanding on the naming of a pressure reducing regulator and a back pressure regulator. A lot of people give the wrong information regarding the naming, and just by looking at the process conditions, we can figure out this is not a back pressure regulator, this is a pressure reducing regulator, or the other way around. Do we see pressure reducing regulators and back pressure regulators in all installations, in all applications? Unfortunately not for us, because only in blanketing situations where you want to control a pressure inside a vessel at a very constant pressure, you see the pressure reducing regulator and back pressure regulators. And in a lot of analyzer systems you see as well pressure reducing regulators as back pressure regulators. But it's important to realize what are we controlling. Regarding the back pressure regulators, I like to say one thing. A lot of people think that a back pressure regulator can be replaced with a safety relief valve or with a relief valve. Please don't do it. You will get a lot of shattering, hammering, and a lot of noises because regulators, back pressure regulators, are built to constantly control a pressure which is too high, so it can easily fend off a little bit and then close again. Safety relief valve or relief valves have a very small sensitive element, and they open, bam, bam, and they close again. So won't work as good. Back pressure regulators work better than safety relief valves. Now, how does a regulator work? Basically, in a regulator, you will find a control element. So we see the seat and your poppet. Seat and poppet, they will open or be closed. And we measure with our load and sensing element. So with the range spring, we control the force on the load on the diaphragm. And with the diaphragm, we measure the outlet pressure. Is there a question? Nope. So I will continue. So if we set a pressure, the inlet pressure will come through the diaphragm, and when the outlet pressure is against the diaphragm, you will try to find a balance with the spring force which is on top. And the spring force, we all know about it because we screw in that knob and we create that force on top. I've got a small simulation of a regulator. So here you see an analytical regulator. You see the inlet pressure, valve opens, there is a flow. And if we unscrew the spring or unscrew the set knob, and so we reduce the force from the spring, the regulator will be closed. A lot of people think that regulators are controlling and opening and closing all the time. Normal regulators in a constant flow situation are working at an opening of approximately 30%. So please be aware that if you do a calculation for a CV value of a regulator, please don't work with the CV values. CV values are just there to compare sizes of a regulator. In a regulator, we control a pressure. We don't control a flow. So if you use a flow control program, so if you use a program which is used to size flow control valve and it gives you the CV value, you've got the wrong value for a pressure control regulator. For a pressure control regulator, will be opening approximately for 30%. So if you use the wrong program, you have to divide your value with 3 and you find approximately your CV value. In my sales life, I did very often get the question, Wouter, I've got this regulator which has a CV of 1. It's not working well. Do you have a better one? Because a competitor made a mistake. Then my question is always, what's the worst case scenario? So we did the calculation. Most of the time we find out that they needed a bigger regulator. So please be aware of this. So in a regulator, we see basically only forces. Which forces are in a regulator? First of all, the spring force. That's the force we create by turning the knob. So we create the spring force by compressing the spring. Then there is a small poppet spring, and that poppet spring should be there because the poppet spring is there to keep the poppet closed into the seat. It's just enough force to keep that poppet closed. A lot of people think that regulators have issues with leakage with high inlet pressures. Now, regulators love high inlet pressures because that inlet pressure force helps them to close the poppet into the seat. So the last two forces we will find is the force and the inlet pressure force. Outlet pressure force, the outlet pressure pushing up the diaphragm, and the inlet pressure force is the force which the inlet pressure creates against the poppet. They all should be in balance. So simple equation. If you change something in this equation, something else has to change as well. Back pressure regulators. How does it work? It's the opposite way. In a back pressure valve, we still create a force on top of a diaphragm. This is your process which you like to control. If the pressure is too high in this process, it will work against the diaphragm. Diaphragm will be pushed up against the spring force based on the set pressure. It will slowly flow away to the outlet. There will be a balance again, and the back pressure regulator will close. Performance of a regulator. We talked before about the flow curve, and again, I like to go into it. The first part of the flow curve is the lock-up zone. We will talk about that. We've got the second part, which is the droop area, and the last part is the choke flow. So we start with lock-up. Lock-up is the performance you see at the regulator when we have a panel, and this is, by example, this is a panel. Over here you see the regulator. The regulator is controlling the pressure. This valve is closed at the moment. You can see that the pressure in the static situation is set at 1 bar. If I open this valve, you will see that the pressure is declining. I selected the regulator with a nice lock-up so that you can clearly see it. So I'm going to open my downstream valve. You'll see when I go from static to dynamic, I will see lock-up. This is the lock-up effect. Each regulator has it a little bit. Do we like it? No, we don't like it. You can avoid it by selecting a different regulator, but this is the effect which we call lock-up. Where does it come from? And again, I go back to the forces. The lock-up comes from the forces created by my poppet spring, the F2, which is created by my F4, that's the inlet pressure force. So the higher the forces, the more force you need to open this valve. So the more lock-up you have. Then another effect, which I also talked about, supply pressure effect. If your regulator is seeing a declining inlet pressure, so again I go back to my pointer, which unfortunately can't use I can use it for this kind of training, but I can't use it for other purposes. So if my inlet pressure drops, my outlet pressure goes up. So in the example I will show you on this panel, in this example, the inlet pressure declines from 4 bar to 6 bar, and my outlet pressure increases from 1.6 to 2 bar. One moment. The outlet pressure. So I will show this in this example. So what we're going to do? This is my regulator. It is set at a certain pressure. It is set at 1.6 bar. I decrease my pressure with this inlet pressure regulator, and we will see that the outlet pressure goes up. So the inlet pressure is decreasing. You can see that my outlet pressure is increasing. So this is what we call factor. And at the pointer is easy to explain it. So inlet pressure goes up, goes down, outlet pressure goes up. And where does it come from? Again, going to the equations. What is changing if my inlet pressure decreases? If my inlet pressure decreases, that's basically my F4. So if my F4 decreases, that force will go down. I'm not touching the knob. I'm not touching my set spring. So something else has to go up. So what can go up? My F3. So basically this equation again explains the balancing of forces inside the regulator. Then the other effect. Regulator flow increases, and what we see droop. And the droop can be seen inside my flow curves. So if we go from this point to a point further on the flow curve, what is happening inside my regulator? My poppet is closing, but the more flow the process is asking me, the more I have to open my poppet. So if you look at my poppet opens away from the seat and my spring gets longer. If my spring gets longer, it loses force. So because of this force I lose at that spring, I also will see the performance of a regulator that we will see droop. And again, going to the equation, my spring gets longer, so I'm losing force on my F1. So what is changing on the other side? That's basically my outlet pressure force. So basically, a spring inside the regulator is the biggest criminal part, because if that spring is selected in the wrong way, you will see more droop. So this is basically the biggest mistake a lot of people make. If they select a regulator, they look in the part numbers and they see the pressure control range. And if you want to control 6.8 bar, please select that regulator. Don't select the 70.2 or the 34. I've been with customers who were proud to tell me I'm standardized on one regulator from your factory, and they selected one regulator which is from 0 to 150 bar, and they were controlling all the pressures inside the plant with that single regulator. And they were basically not happy with the performance. And I can explain, because basically they were looking for this light spring and they were using this strong spring. And so with a strong spring you will see more droop and you will see more side effects. So please select your regulator exactly according to your outlet pressure range. Your loading elements. A lot of people select regulators based on the spring, because most people know spring-loaded regulators. And the spring-loaded regulators, we have been discussing them, but you can also use dome-loading regulators. So the only thing you do with a regulator is creating a force on top of a diaphragm. You can also create a force on top of the diaphragm with filling this area with pressure, with a compressed gas. And if you create a force with a spring, you can also create a force with this gas in here. And basically, if you create a pressure in here of 5 bar, so in this dome 5 bar, you will get 5 bar out. So this is a typical example of a dome-loaded pressure regulator. We create a force on top of the dome. This is a typical example of a nice big dome loader. This is the inlet side, the other side is the outlet. We take the pressure from the inlet, we reduce it with the pilot, it goes into the dome. Because we like constant outlet pressure, we bleed the pressure back into the system. So what is the big advantage of using a dome-loaded regulator against a spring-loaded regulator? Like I said, I like to see a big, nice diaphragm. And the ratio between the size of the diaphragm and your seat is basically also influence your supply pressure effect. So the effect of pressure goes down, outlet pressure goes up. So if you have with a dome-loaded regulator, we don't change from diaphragm size. It will always be the same size. So we don't go to a smaller size poppet or piston. So over the full set pressure range, we have a nice, big, large diaphragm. So we have a low supply pressure effect. We have no spring, so we have lower droop. And it's possible to do remote control. Think about a situation where you want to control pressure far away from you. You can work with an electronic pilot on top. And the people online, Proportionaire, they know what to do with remote control. So this is the main reason to work with diaphragm regulators and dome loaded. So another regulator we supply is a mix of dome loaded and spring loaded. So what we do in this regulator is we have a spring, that we call it a bias spring, and we have a dome, so this area. So what you can do with this regulator, we have an inlet, we have an inlet pressure, we have an outlet pressure, and the outlet pressure can be controlled first of all with a constant bias. So if we set this spring at 5 bar, there will be always 5 bar coming outside of the regulator, but with an external source, and by example in a mechanical seal, we can have the pressure from a pump, and that pressure from the pump can go inside my dome. So if I always want to have like 2 bar more on top of my seals, I can work with a differential pressure regulator to use the differential pressure regulator. So this is a mix of dome and spring loaded. So best practice. And this part is, for a lot of people, is it common sense and daily business. But I like to emphasize this part. A pressure regulator is a control element. If a pressure regulator is controlling high pressure, like 3000 psi to 1000 to 100 psi, the risk of having a small leakage inside a pressure regulator is always there. If it's brand new and it's really it's tested in the factory, all our regulators are 100% tested when they leave the factory. They must be bubble tight. But even in the installation or even during commissioning, a lot of dirt is still in the system. The dirt comes into the seat, and it can damage your poppet and your seat. So in case there is leakage, what you call creep, it's possible that your outlet pressure is leaking through the regulator in the downstream area. And during normal use, you will not see this. But if you stop a process during the night and you keep your full inlet pressure at the regulator, and you don't control or you don't put safety devices in your downstream area, due to creep and leakage, it's possible that your inlet pressure becomes outlet pressure. So do we like this? No, of course not. But we have to realize that the pressure reducing regulator is not a shut-off valve; it's a control element. So what improvements can we make? First of all, filtration is I would say the best protection for a pressure regulator. Having a relief valve installed in a downstream system, sound engineering, fully common sense, but we don't see it very often. So install relief valves downstream, and the best thing you can do is buying a regulator, but also buy spare part kits. So if you have got a spare part kit available and you have an issue by damaging your seat, you can replace your seat. This is basically the thing I want to talk about today. So if you select your next regulator, be sure that you have all your process information, that you know your inlet pressure and your lowest inlet pressure, that you know how accurate your regulator must be, that you realize, are we controlling upstream pressure or downstream pressure? Do I need a pressure reducing or do I need a back pressure regulator? Since today you know about Droop, lock-up, supply pressure effect. So a regulator, you like to see the regulator having a constant flow curve, but it will always be a little bit of droop or a little bit of effect. So do we need a spring-loaded regulator? Can we work with a spring-loaded regulator, or can we work with a dome-loaded regulator? Or maybe do we need a mix of both? And then step 5, did we take all the precautions to protect our system for damage and overpressurization? So these are the steps. And if you take them, you can be sure that your next regulator will be an absolutely good choice. So I wish you all the luck in selecting your next regulator, and thanks for listening to me.
Oh, thank you, Wouter. And we can address some questions now.
Yes, of course.
Okay, well, to give you recommendations for when using oxygen.
When you're using oxygen, oxygen is let's say a scary medium, and on the low pressures and in the low flows and the low velocities, you can select stainless steel. But if you really have high velocities in your line, you make a design mistake. But we have some regulators which are made from brass, which can be used and are approved for oxygen. So brass material and Phyton seat and Phyton seals. That's the one you need.
Okay.
Any other questions from that have come in, Mike?
I do not see any other questions.
Yeah. So I'd like to encourage any questions from the group at all, please. Feel free to send them through the chat box.
Yeah, the question is, will we receive a copy of this presentation? I believe that's correct. We can send out this presentation was recorded, so we can send that out.
We can send the link. And again, if there is any question regarding the pressure reducing regulators, the first way to go is go to your local sales and service center in Indianai, Cincinnati, and ask the question to your sales representative.
Yeah, one question we have about oxygen again is, do we note when items are oxygen cleaned?
Yes. And so when regulators are used in oxygen, we basically clean them according to ASTM G93 level C. So you can order regulators which are cleaned with that level. So we can clean it according to that level, and we basically our machines are tested, or cleaning baths are regularly tested to be sure that it's done in the correct way.
Okay. And then another question we got is, what is the difference between using a dual stage regulator versus two separate regulators?
It's a dual stage regulator or two separate regulators. There's no difference. The difference between a dual stage regulator is, people talk about a dual stage regulator when two regulators are built in one body. So two regulators are internally connected, but those when we have a KCY regulator in our program, which is a 1/4 inch connections, and that is basically two regulators in one body. If you take these two regulators apart in two regulators, you have two regulators. And basically, if you take two 1-inch regulators and you put them in series, you have a dual stage system. In CNC, we very often see like two big dome-loaded regulators, 4-inch regulators in series, and sometimes they have two redundant regulators as well. We don't have two 4-inch regulators in one body. So basically, it's exactly the same. The biggest difference is there is a length of line in between these two regulators.
And question, what preventive measures should be used to help prevent cavitation in the regulator?
If you want to prevent cavitation inside the regulator, first of all, try to prevent big pressure drops. So if you do multiple steps of reducing, that's basically the best way to prevent cavitation. In flow control valves, very often there is a cascade system behind the seats. That's very difficult to make that inside a pressure control valve. So my advice is take multiple steps to avoid big pressure drops. And the medicine which is used very often is like a special seat material, hardened material. But basically, that's a kind of medicine to avoid the cavitation. But in my opinion, it's always the best you can do is prevent big pressure drops.
All right, thank you. That I do not. Oh, one more question. What suggestions do you have or pitfalls to avoid in using an electronic piloting valve for a dome load regulator?
To be honest, to use and to let's using an electronic device or electronic regulator on top of a dome loaded regulator is a great advantage of it. Is you can do it remote, you can do it very precise, you can control, you can create an external feedback. So you can basically have a dome loaded regulator, have an electronic pilot on top, control the pressure inside your dome, have a second pressure indicator downstream. If the pressure drops a little bit over there, you can give a signal back to the electronic pilot, so you can make like a closed loop. So with the use of the correct electronic pilot on top of a dome-loaded regulator, you can basically create a very flat flow curve. You can compensate for most of the errors I talked about today. And we do supply them. I hope that answered that question.
Yeah, we have time for a couple more questions. If anybody wants to submit some more questions, we have some time. Anything else coming in, Mike? Here's one.
Any comments about various heated regulators to avoid freezing up?
Yep. So freezing up of regulators. So very often in a case where there is a risk of a freezing regulator, if it is a small regulator with a small flow inside an analyzer system, very often we can use our heated regulators, which have an internal element which basically heats up the gas before we reduce it, and so to keep the system away from freezing. If we talk about bigger units like in gas supply streets or virtual pipelines, very often the best advice is to have like a heat exchanger before every step you install. So heat your gas, reduce the pressure, heat your gas, reduce your pressure. So if the gas comes in at 21 degrees, sorry for the Celsius, but if it comes with a certain pressure and heat it up so that it comes out in the correct in the 21C, and if there is a second step, do that again. So my advice is to heat up before each and every step. And Joule Thomson is an effect which is there. So especially on bigger systems, you need a good heat exchanger. And we can do calculations for the wattage we need. So on the analyzer systems, you can tell us this is our fluid, and these are the pressures drops. So we can calculate how much wattage you need to heat it up.
Okay. And the comment was, preheating the gas. Thank you.
Okay. So I answered the question.
Yeah.
Yes, don't forget that we're raffling off the Jedi cooler, so please keep the questions coming.
When blanketing solvents, do any additional consideration need to be made if there are extended periods where there is no draw on the tank and therefore no nitrogen flow through the regulator? Any issues resulting from condensation of solvents and regulators?
So if we have a blanketing system, on a blanketing system, we have our blanketing regulator series. So it can be set at low set pressures. And so the set pressures of these two regulators are set very close, and we can set them close because of the big diaphragm. If you are working with solvents, my advice is always to select the Calres seed material inside the regulator so that you avoid chemical attack of the sealing material, especially on the vent regulator, because the blanket on top of the solvent is always full with chemicals. And so if you vent it away to a safe place, it's very advisable to have like a material which is compatible with your solvent. And it's not as important as your inlet pressure regulator, because it only sees the clean gas coming in and going in your tank. I hope that answered the question.
Yeah, we'll give a couple more minutes here if there's any other last minute questions.
So, and I think the additional information I can give you to talk about regulators, to train on regulators, I can talk about training on regulators for a full week. So what we did today was just a very compressed information about our what we can do with regulators and what you have to think about. But if you want to know more about regulators, we can supply you additional training and additional information.
Okay.
So,
And one more question popped up here. In a location with temperature variation outside, should a regulator be sized larger due to this variation to reduce, and the word is fluxion, I assume they mean fluctuating pressures.
In general, so temperature. So if we come to the temperature and where I said compatibility, so your material should, first of all, your material should be compatible with your lowest and highest temperature. It could be in a very hot environment, in a very cold environment. So that's one thing you have to consider. And the other thing is if you work with different temperatures, if you heat up a gas, it gets more volume. So you also have to calculate what you are doing. So if you go for an extreme high temperature, you have to basically to figure out your worst case scenario to size your regulator. So it's something you have to consider, absolutely. But the good thing is most of our regulators are used in temperatures from, let's say, from 20 to sorry for the Celsius, from 20 to 80 degrees, and because we talk about Kelvin in the first gas law, we talk about Kelvins and not about Fahrenheit or Celsius. The biggest differences are not that much. So it is something to consider, absolutely, especially if it is at the sharp side of calculation, the size of a regulator.
Okay. And is there any, I assume the question is there any explosion-proof regulator?
All the regulators, I would say most regulators except one is our regulators are all mechanical instruments, so not connected to wires. The only regulator which is connected to a wire is the KEV, which is a heated regulator, and that regulator is an ATEX approved regulator, so we are safe on that one. And as soon as we want to control the regulators with an electronic pilot, then we have to consider the ATEX approval on that electronic pilot. But we can get electronic pilots as well. So we have basically we have a standard supply for our pilot regulators, and we can use an ATEX approved one from them.
Response was thank you. So yes. So I do not see any more questions coming up.
Okay. Well, if there's not any other questions, this leads me to say a special thank you to you, Wouter, for sharing your knowledge of regulators. And in fact, a special thank you for everyone who attended today. So from all of us at Swagelok, Indiana, Cincinnati, we look forward to having you join us again for our next webinar, which will be on gas distribution systems, and this will take place in January. I encourage you to please keep a watch out for your inbox for more details to come. And as always, please share these webinars with anybody else within your organization. We really appreciate your attendance. Thank you very much.